When astronomers look for evidence of life in the universe, there's a bit of a problem. We only have one example of life here on Earth. We don't know what life might look like on other worlds because we've never found it. But when you think more generally about Earth-sized world in the habitable zone of their star, we actually have two examples here in the solar system, Venus and Earth. And as you know, Venus is Earth gone drastically wrong. And yet it is the same size as Earth, has the same gravity, same mass. It's very similar. And yet so many things, its temperature, its orbit, they're all totally different from our planet. And so thinking about Venus and thinking about Earth allows us to study exoplanets and get a better sense of what it is that we're looking at. And when we start to discover tens, hundreds, thousands of exovenuses in other star systems, that will help us understand the history and the story of Venus itself back here in the solar system. So it's a very fascinating connection between Venus and exoplanets, exoplanets and Venus. And so my guest today is Dr. Michael Way, who is with NASA's Goddard Space Flight Center, and he focuses on the atmosphere of planets, trying to figure out how we can learn more about the atmosphere of Venus and how that'll relate to exoplanets. It's a fascinating interview. Enjoy. Before we even started the interview, you surprised me with a fact that I didn't even know about Venus. It has subduction zones?
Well, we believe that this thing you're seeing behind me called Artemis Corona is a very large subduction zone, actually. Yes. Not in this exactly the same way that Earth subduction zones work. The way this subduction zone works is a bit different, but we do believe that this zone can collapse and bring material down into the mantle, basically into the lithosphere mantle in this particular subduction zone. So yes, Venus has all kinds of surprises for us. People think of Venus as a stagnant lid planet like Mars, but there's a lot of controversy with that statement. Not everybody agrees that it is a stagnant lid. People think it's in a different kind of tectonic state.
Now Venus is really exciting, partly because it is essentially another Earth. Same mass, same gravity, and it's right next door. And yet it's filled with mystery, which makes me worry about our ability to understand exoplanets very well. How sort of make this connection about Venus as an exoplanet?
I think you're absolutely right. Venus presents us with a lot of unknowns. Part of that is because we really haven't explored it nearly as much as we have Mars. And therefore, we don't have that much data. So as I always like to joke with my colleagues, I like to work on Venus because the parameter space is large. So you can come up with a theory. You know, I even have a paper a few years ago that's a hypothetical climate history of Venus. Certainly 99% of it is wrong, but it's fun to play in that kind of sandbox. So yeah, we think that, you know, Venus and Earth might have started out in very similar ways. As you point out, they're very similar in mass and size. Unlike Mars, everybody thinks Mars is, you know, some kind of Earth, but Mars is very, very different from Earth and Venus. Earth and Venus probably had similar thermal histories in their interiors, meaning that they might have cooled in similar ways over time. And they might have started out very similarly, although we don't know for sure because the proximity to the sun does play some role in their very initial post-accretion stages, you know, the stages right after they formed. So yeah, there are a lot of mysteries about it. And exactly kind of what you were saying, you know, we're not convinced that when we find exoplanets in the orbits of Venus around G-type stars, that they're really going to be Venuses. They might be Earths. Mm-hmm. We just don't know. We don't have enough data yet, but there are those hypotheses out there that we're trying to explore.
And when I think about the controversy about even, say, the discovery of phosphine in the atmosphere of Venus using some of Earth's most powerful radio telescopes, and people disagree. And some people say we found phosphine, and other people say, have you really? And yet Venus is right there. It is pretty much the closest planet to us, and yet even with all of these powerful instruments on an object that is merely tens of millions of kilometers away from us, we're not able to get a conclusive answer to this question. Do you think, like, not to mention stuff that is tens of light years away from us? So do you think that we'll be able to crack the mystery with Venus, and how hard is detecting biosignatures on exoplanets based on what we're learning?
Well, I think I think we will eventually crack the mystery of Venus, but it's just going to require a lot more missions. And as you know, Venus presents a very challenging problem to get to the surface as compared to Mars, right? Mars is a very thin atmosphere, low gravity, and Venus is the complete opposite. The bottom of Venus is a 90-bar atmosphere, so it's 90 times the density of Earth's atmosphere. That's about the same as being 1,000 meters under the bottom of the ocean. That's the kind of pressure you would feel there. It's also, around 550 degrees Celsius on the surface. They always say enough to melt lead. So to put something on the surface of Venus is extremely challenging, but that's what we really have to do to really understand fundamental aspects of it. There's several things we need to do. We first need to fly better mass spectrometers in the atmosphere to really understand what the atmosphere is made out of and how it got to be the way it is today. So that's a really crucial thing that we have yet to really achieve. We've flown one mass spectrometer, as we understand it today, in Venus's atmosphere, and that's it, basically in the 1970s. So we're going to fly a new mission called Da Vinci that's going to fly out of Goddard Space Flight Center that's going to make much more precise measurements. So those are just the baby steps. We're going to make these initial measurements. We're going to have some really nice radar mapping and infrared mapping of the planet's surface that's going to come from two other missions, one called Veritas that's run out of JPL, and another one called Envision that's run out of the European Space Agency. So I think all of us in the Venus community are extremely excited about these new missions and what they're going to tell us about Venus's history, but they're not sufficient. We're going to have to run follow-on missions, and we're going to have to develop completely new technologies. So the class of missions that we're flying now are not really expensive enough, is one way you could say it.
Flagship enough.
Yeah, exactly right.
Yeah.
We don't have enough money to develop completely new technologies. We have to rely on what, as you know, are called legacy technologies. So the mass spectrometer that we're going to fly on the Da Vinci mission is very similar to one that we've flown in Mars. So we really need flagship type funding to really go to the surface and really deeply understand it. I mean, even to the point of maybe even, digging samples, things very similar to what, Curiosity and Perseverance are doing on Mars today. But we're decades away from accomplishing that. It's very difficult. There are other ways we can do things on the surface to measure rock types and stuff like that, but it's really challenging. And we also need to go to, I think, what many geologists consider are the most interesting regions of the planet, and that's this stuff we call tessera, which are these highly deformed features on the surface, which look like the oldest sort of surface units on the planet, but we're not completely sure. It just looks like 80% of the surface has been resurfaced in the last roughly 500 million years. And those tessera look like they're being embayed by these basaltic flows that we see on the surface. So we think that they're older, but it's very difficult to land something there. We need really high resolution radar data that we're going to get from the Envision mission, so we can put a lander there that doesn't land and then topple over and break its radar antenna, and we get nothing.
Right. I mean, like, even if you got incredible, okay, so I mean, like, think about what happened with Perseverance. Like, they knew that they wanted to send Perseverance to the most interesting place they could find on Mars, and it wasn't necessarily the safest place to land a spacecraft, so they taught the spacecraft to find a good landing spot. And so I think you would need to do that while at the same time the spacecraft is in torturous, going through this horrible environment at the same time, to try and hold it together, keep its electronics rolling as the temperature and pressure increase. So it's just like next level of complexity.
10 levels of complexity.
10 levels, sure, fine, yeah.
I think you're right, that you're absolutely right about Perseverance, but I think it was clear that they would find some place to land not that far from, inside their error ellipse. But what if you get to Venus and you don't find a spot
Mm.
like that? And you've spent $5 billion to get there, for example.
Mm-hmm.
So you really want to get as high resolution information as possible on the surface to know there's got to be somewhere flat where I can land. And yeah, there'll definitely be some small scale maneuvering, but you're right, you won't have a lot of time, at least as we understand the way we're going to fly missions today. So it's very, very challenging. Absolutely.
I mean, I think about the work that was done with, the OSIRIS-REx mission, scanning the surface of asteroid Bennu down to centimeter resolutions, mapping every single rock, finding exactly the gap that was big enough to land a spacecraft. I mean, is that the level of precision that you're hoping to be able to build?
I don't think we need necessarily that level of precision, although funny enough, we will get some of that from the Da Vinci mission as well. Because not only is it going to measure the atmosphere as it falls through the atmosphere, it's going to have an imaging camera at the bottom. And as the PI for the mission, James Garvin always likes to point out, we're going to have, images down to the centimeter resolution just before it hits the surface. They're going to have photos.
Right.
So
it'll see the centimeters that are below its cameras as it, as the dying part begins. Yeah.
Yes, exactly. So at least over Beta Regio, where it's going to come in, we'll have pretty good, infrared images as it falls to the surface. And the other thing that's going to also provide us is sort of the first ground truth for the orbiters, because the orbiters are also going to have infrared cameras that can look through windows in the atmosphere, and it'll have a direct connection to those orbiters. That's going to be really, really powerful. And I know I'm talking much more about Venus and the exoplanets, but
no, it's fine. It's fine.
Really key. It's really key.
Yeah, so I guess what would it like? I'm happy to talk about either, and I think right now I want to talk about Venus, so that's fine. And I guess what would it take to get the kind of resolution? You talk about flagship, and we talk about it being many times more difficult than Mars. I mean, obviously with Mars, there's just almost vacuum between your spacecraft, the Mars Reconnaissance Orbiter, and the surface of Mars, while there is just this horrible thick atmosphere between an orbiter and the surface of Venus. So what is the technology that gets you that high resolution?
Yeah, so the idea is that we're going to do a radar map, a much higher resolution radar, global map from a mission called Veritas that's going to fly out of JPL. Mm-hmm. So the idea has always been these missions are all sort of linked. So Da Vinci and Veritas will fly around the same time. At least originally that was the idea. Now there's some delays for Veritas. It's not clear what's really going to happen in the long run. But there's several things going on here. So first, as I said, Da Vinci, as it falls through the atmosphere, is going to take these infrared images, and they're going to tell us what we see on the surface and what that corresponds to with Veritas's high-resolution radar and its infrared imaging.
So kind of like Huygens.
For the first time.
Like Huygens.
Kind of like Huygens, yeah.
Seeing images of Titan surface and then being able to then think about Cassini's images and map them one-to-one.
I think that's exactly right. I mean, it's very, very similar. Exactly.
Right. Okay.
So we'll get that. First, we'll do a much better job of characterizing the surface from orbit. That's what we're going to see with Veritas and Da Vinci. And then Envision is going to take the Veritas maps, which are much higher resolution than the old Magellan maps from the 1980s. And they're going to decide, the science team's going to decide, okay, where are the most interesting regions possibly for landers? And I think they have 3 different resolutions on their radar imaging plan. And the highest resolutions will go in those really, really interesting areas that we'll have characterized a bit from Veritas and Da Vinci. So that's the idea between those 2 missions. And of course, I don't want to leave anybody out. There are some plans for the Indians to also fly a radar mission, not so different from Veritas. And even the Chinese have discussed flying a similar mission. I don't think it's been approved at their National Academy of Sciences level, but it's possible that they will also fly. So who knows? In 10 years, we might have 5 orbiters flying around Venus.
Yeah. It is weird what a collection, a traffic jam of spacecraft there is at Mars, and yet almost nothing at Venus. And so give us a sense of scale. You've got the Magellan images behind you. What was the resolution of the radar system on Magellan compared to what could be possible with Da Vinci and what could be possible with even a future flagship mission?
Yeah, well, I mean, first of all, the Veritas mission is going to be, I think, roughly 2 orders of magnitude higher horizontal resolution, and I think similar in the vertical. For flagship, I mean, I think for most of us thinking about these things, I think the flagship is really going to be more about sampling the atmosphere and getting to the surface. So, as I said, we're going to build on these higher resolution maps from Veritas and these super high resolution maps from Vision to tell us where to go on the surface. That's really the idea here. So, what that will look like, we don't know because we don't have a budget and we haven't been selected yet. So there's a lot more work to get to the flagship mission. We would hope that the flagship might, get in the next round or the round after that and might fly in, say, 15, 20 years. But when exactly, we don't know yet. Right. But certainly the idea is to get to the surface, I think.
And so let's talk about that in situ sampling of the atmosphere. So what would that look like? What would be sort of your ideal mission to be able to actually measure the gases in the atmosphere itself?
Well, I mean, I think Da Vinci in many ways is the ideal mission. I mean, it's going to just be a high resolution neutral mass spectrometer. So it's going to really sample the atmosphere, at high resolution all the way from the top to the bottom and really understand, what are the different isotope ratios for different species that tell us about the evolution of the planet and give us a handle on what's really been happening there. And also to help us really understand, for example, is the atmosphere well mixed? There is an idea that the atmosphere is well mixed and that carbon and nitrogen and all these other species are well mixed, but there's some evidence from the original mass spectrometer that flew on the Pioneer Venus mission that may not be completely true. And we also see some things in the data we have from other orbiters on the planet, around the planet, that are telling us that things might not be quite as simple as we think. And then, of course, as you pointed out, there is this phosphine measurement. There's a lot of argument about that. One team seems to always find it, and most other teams do not. And that also is probably telling us something about, understanding this upper atmosphere and what we're seeing there, and the resolution of our images and our methods, on our approaches, basically.
So long-term analysis in the atmosphere of Venus is of no interest to you?
No. Of course, one thing I left out, sir. One thing I also left out was that one of the ideas is to fly a long-lived balloon mission.
Right.
And that can be very interesting from several aspects. One is, of course, to understand circulation patterns, and again, to understand, how our atmospheric constituents changing at the cloud level, for example. And the other thing that they want to fly on a balloon mission is a very sensitive magnetometer, so that we can see if we can detect any crustal magnetic fields. So, as you know, Mars today doesn't have an intrinsic magnetic field like Earth has, but we can detect the remnants of the magnetic field in the crust. So there's these very strong regions, these strong crustal magnetic fields that we see on the planet. Whereas on Venus, we've never detected a magnetic field of that kind on Venus thus far. We've never detected any remnant magnetism. And that's a bit confusing in some ways to us. So I think that is could be really interesting. If we can detect crustal magnetism on Venus, that tells us that the planet once had a magnetic field. And that's very interesting in itself, because we're very confused, I think, why Venus doesn't have an intrinsic magnetic field. Many people think it's because, I would say many lay people think it's because it spins very slowly. But according to people who do those kinds of simulations of the core, they say no, the planet's spinning plenty fast for it to generate magnetic fields, yet it does not. Now, it does not have one today, but maybe it had one the day before Mariner 2 arrived in 1962. Or maybe it had one 1 billion years ago, or maybe 4 billion years. We don't know that. But if we can get really sensitive magnetometers flying, much closer to the planet, we might detect some crustal magnetism. But on the other hand, we may not. Because while the current surface is below what's called the Curie melting point for those materials, meaning that if you get above the Curie point, all the magnetic field lines rearrange themselves and you don't see anything. But if the planets stay at the same temperature or lower than that, then there probably will be some crustal magnetism. But if we get there and we really find nothing, that means one of two things. One, the planet never had a magnetic field, or two, the surface did get even hotter than it is today, and all of this information was lost, basically.
And so I think about that process of like paleomagnetism, like where people can go and study lava flows here on Earth and detect the alignment of the magnetic field. And so that process, you can detect that from the air and not necessarily have to be grinding up pieces of rock in the lab and figuring out the magnetic field.
Right. We do it on we do it on Mars, excuse me. Yeah, we do it on Mars. We have in-orbit magnetometers, and we can detect these crustal magnetic fields. But the ones we've flown for Venus so far have never detected any crustal magnetic field, and that's a big mystery.
Right. And so I guess with that idea of the atmospheric mixing, if the atmosphere is mixing up quite well, then one pass through the atmosphere with Da Vinci should get you a representative sample of the entire atmosphere no matter where you would go. Like, you wouldn't learn a lot more by loitering in the atmosphere at different altitudes for long periods of time. It might be better quality, but it's essentially going to be the same story in more detail.
You're right.
Which is
exactly. If the atmosphere is well mixed, but if the atmosphere is not super well mixed, then it might tell us other things. Although I think, it might be that the atmosphere is not well mixed vertically, but is well mixed horizontally. So again, if Da Vinci, that one might be enough to tell us, okay, we really understand the vertical profile. We don't expect the horizontal profiles to change so much. But we could be wrong about that. We'll see. We'll be able to compare what Da Vinci gives us to this old Pioneer Venus data, because certainly they'll come down in different places, and it'll give us some indications of what's going on.
But like, one of the tricky things about Mars is detecting the outgassing to maybe help explain some of these methane detections. I mean, that would be incredible if you could detect some kind of outgassing on Venus.
I think there is a growing consensus in the community that Venus is outgassing stuff. For example, we see a lot of sulfur dioxide in the upper atmosphere, and it's believed that sulfur dioxide is produced by volcanism. And if you shut off the volcanism today, I think one of the calculations says that within 1 million years, there'll be no sulfur dioxide in the upper atmosphere, for example. So, and there have been other observations that look like there's active volcanism on Venus. So I would be shocked if we didn't find active volcanism on Venus, frankly, given what we think we understand about the planet, its thermal history, and how we understand volcanic processes on Earth.
Right. All right. So we've talked about this flagship mission. I'm sort of envisioning this sort of Battlestar Galactica style orbiter that is launching out a fleet of balloons into the upper atmosphere to map that all out. So it's got the surface scans, it's got the atmosphere scanned. What would the lander component look like, do you think?
Well, at least in the previous iteration that people have submitted, it would look not that different from the former Soviet Union type landers. I mean, a very large sort of bathysphere, something like that would land on the surface and keep the instruments cool for a few hours in order to make some sort of X-ray scanning of the different rocks and try to understand what the different rock materials are on the surface and things of that nature. I mean, that's much higher level geology than I'm an expert in. I'm really an atmosphere person, but that would be the idea.
But a few hours, I mean, that's sad, right? Like,
well, I mean, it's very warm. I mean, there have been some other technology, some investigations that use different kinds of materials that would keep the lander going for much longer. Other ideas, which are really fascinating and could make it in such a mission, would be to have a balloon platform that can go up and down. So maybe you go down, you grab some stuff, and then you get out of that hot stuff, like dipping your toe into a hot tub and then getting out. Then you do your analysis up there, and then you go down again and get some more stuff. Yeah, exactly. I mean, that's the really super cool stuff that people are interested in. Would be something like that. Although we've never built something like that on Venus, so that's the hard part.
Right. Well, like we're just imagining here. There's no constraints. Nobody from NASA is going to listen to us and secure funding.
Well, you have to be careful because Lori Glaze, who's the head of Planetary Science Division, is a Venus person. So if she watches this, I'm going to get
okay. All right.
I'll be fired next week.
No.
Mike.
But the I know, like, on the one hand, there's this research into the materials that can handle high temperatures, even the conditions and pressures of Venus, and still be a computer without just turning into a pool of silicon and aluminum, right? So do you find that side promising?
Yeah, I mean, there has been some work on different kinds of chip components that could withstand high temperatures. So there's several programs on that. There's also been some work on, there's a program at NASA called High Temp. No, oh, I got the name wrong. But anyway, there is a program that tries to look at high temperature electronics and other things that can survive in the Venus atmosphere for a long time. And that's already allowed us to look at some long-lived kind of surface instrument things that can tell us like pressure and temperature and can stay there for a long time. They basically don't melt or anything like that happens. Another thing that they've done research on is Hot Tech. That was the program's name. Sorry. Another thing they've looked at are in these kind of bathysphere type systems where you have a material in the bathysphere that kind of breaks down over time. And as it breaks down, it provides some kind of cooling. And that can keep you going for much longer than you would in the conventional case where, it's just cool as it comes down and then it just heats up over time and then your stuff melts. So several different approaches to longer lived instruments on the surface. But I think for example, one program is called LISSI. It's long-lived surface environment or something like that, where they'll have these little boxes that come along and they can just hang out on the surface. And maybe you can even have seismometers on them, similar to like we have on Mars today. And they can just sit there and they could last for as long as the photovoltaics last, if you have photovoltaics, or just batteries, as long as the batteries last. Or maybe we'll develop other technologies to allow us to, hang out on the surface even longer.
There was really interesting research into clockwork type devices that would do this mechanically. And so you wouldn't necessarily need to have computers. It would all just be done in mechanics. So I wonder if any of that has borne any fruit.
Well, I mean, I think that's at its initial stages. There have been some, as you say, mechanical things. And I think that on the top, they have some kind of disc that spins and it provides a kind of a signaling mechanism for example, a radar instrument or something like that to tell you where it's going and what kind of inclination it's found. But I don't know how far we can go with that technology. I think we're at our infancy in a sense. Again, I mean, we haven't been to Venus for a long time. There's never been like a dedicated Venus research program like there is for Mars. So we just don't have that legacy of decades like we have for Mars, thinking about different approaches to the surface. But I would say that all these new missions going, Da Vinci, Veritas, and Envision, are spurring a lot of innovative thought, which we have not seen for a long time, not, I think, since the 80s. So it seems to me like every other week, I either see a paper or I get asked to review a paper about some crazy cool idea to do this or that on Venus. So I think that's going to drive a lot of interesting development in the longer term, as long as we can find some kind of pots of money to fund people to continue these kind of studies. And then by the time we get to the point of thinking about a new design for a flagship, we'll have all that legacy, which we can then try to move forward with.
Well, the thing that I find really exciting, like because it's so complicated, so hard, and essentially impossible on a lot of fronts, it brings up the most creative ideas. And it feels very similar to when people are talking about interstellar flight. Like, it will take us tens of thousands of years to fly to the nearest star. But what if there's a way to do it faster? Okay, and then people will throw all of these really creative ideas on the table and just start to mull them over one at a time. And it's quite surprising, some of the really clever ideas that come out of that process when there's nothing to lose because it's so hard. And I think Venus is very similar to that. It's such an exciting world. As we started this interview, so similar to Earth in so many ways, and yet so inaccessible. It is like trying to get to the bottom of the ocean on Earth and move around there, and yet it's another place. Also hot, also sulfuric acid. Anyway, awful.
Yeah, I mean, I think you're absolutely right. So, I mean, one of the things in this paper that we try to do is explain how, and I think many chapters in this book that our paper is a part of is really trying to leverage what we understand about Earth and try to apply that to Venus. And then also explain to the exoplanet community that these are the things that we kind of expect or might expect, and those are the things that we need their help with, for example. So, for example, understanding the very early history of Earth can tell us about possibly the very early history of Venus. And if they're very similar, that tells us what kind of observational constraints we can place on things. So for example, we believe that in this post-accretion phase, after the Earth assembled all of its parts before the moon forming impact, the planet would have cooled down fairly rapidly, we think, such that the atmosphere, whatever it was consisting of, probably nitrogen and carbon dioxide and maybe some water vapor, we believe that that would condense out on the surface very early, and so we get our first ocean. So a very early Earth would look like an aquaplanet, completely covered in oceans, for example, or mostly covered in oceans. Now, if we look at Venus, there are different theories about how its early evolution happened. So did it happen the same as Earth? So in this post-accretion phase, it cooled down fairly rapidly within a few million years, and then water would condense out on the surface? Or because it's a little closer to the sun, did that cause the atmosphere to stay hotter longer, this atmosphere that it had, whatever it was, again, nitrogen, carbon dioxide, steam, and that would keep the surface molten longer. So you support this kind of what we call a magma ocean atmosphere. So the surface is like a magma, live lava, and over that you have this atmosphere. And so those hypotheses tell us that if this atmosphere stays around for a long time, a lot of your water budget might be in the atmosphere, right? And what happens in a case like that? Well, in the very early history of our sun's a bit more active. It has more ultraviolet and more X-ray radiation coming off it, not to mention CMEs and all this kind of nasty stuff. But the key thing is that the water vapor in the atmosphere can be photodissociated by these very high energy photons. So your water molecule gets hit by these photons and gets dissociated. So the hydrogen separates from the oxygen, right? And in this situation, your hydrogen can escape very quickly. So we have a section in the paper about escape on the planet and trying to understand escape. So imagine that in the beginning, this atmosphere stays around for a long time, all your hydrogen escapes, then you have all this oxygen left, it recombines as O2, it sits around. Some of that will go along with the hydrogen, but most won't. And the current hypothesis is that in a situation like that, the oxygen would be absorbed by the magma ocean. That's really interesting, because that changes what we call the redox state of the planet itself, the bulk planet. That means it's a lot more oxygenated in the interior of the planet, and that will affect what comes out later in its history, for example. Maybe nitrogen comes out more readily than it would for Earth. For example, Venus has 4 times as much nitrogen in its atmosphere as Earth has for its mass, right? Why is that? Why is it like that? Why does it have all this nitrogen? We don't understand that. So you have this situation where maybe that's how Venus started out. This strange atmosphere in the beginning, in the post-accretion phase, stuck around for too long, and it lost all of its water very early on. So we have those kind of 2 scenarios, and that's where the exoplanet stuff can come into play. So imagine someday, it'll be a long way down the road, but let's say we find a planet in the Venus zone 50 million years old after it's accreted. For example, let's say there's some way we can figure out that number. It'll be very difficult. And it has this crazy steam atmosphere still sitting around, this magma ocean still going. That probably tells us that hypothesis for the long-lived steam and CO2 into atmosphere is right, and that these planets cannot be Earth-like. Or what if we see that it does have, it's an aquaplanet, it's sitting in the Venus zone, and all of our theories about how these things work are wrong. And we start finding Earths, but not at Earth, but at Venus. Or we find the reverse. Some hypotheses are that, it's very tricky to get Earth to where it is today because so many things have happened throughout its history. What if we find an Earth-like planet where Venus sits and a Venus-like planet where Earth sits? That would be wild.
Yeah.
So that's what excites a lot of us, I think.
I think the astrobiologists have one sample. They have Earth. They only have one place that they know of that life formed. Right. And so everything they do is trying to extrapolate from this one example. But in the case of Venus, we have 2 Earths. We have 2 Earth-sized worlds within the habitable zone of their star. And that ability to do that comparative analysis between these 2 planets has got to feel like you have almost an infinite amount more data than the poor astrobiologists.
You're absolutely right.
And from there, as you say, as you study these exoplanets, hopefully we'll find all of the gradients in between. The Venus-like planets that are out of the orbit of Earth, the Earth-like planets that are within the orbit of Venus, and the Mars-sized world that's snuck in between, and every shade in between, and start to really piece together that story to help you study. And so by studying exoplanets, you'll understand Venus.
Yeah, that's the idea. I mean, I guess Venus is much more accessible, sort of. but we're always going to know more about Venus or Earth or any planet in the solar system than we're ever going to know about any exoplanet any time in the near future.
Yeah,
that's really the reality, right? But as you say, if we can get enough data from the exoplanet realm, maybe we can understand at least the demographics in a sense, like what's the probability for these things happening? And do we see that their evolutionary histories are similar to what we think they are? Or, can we explain how Venus got to where it is today? And maybe even better explain how Earth got to where it is today. And I think that's the big, sort of holy grail for us in a sense. If we can get that in the next decades, it's going to really help us understand. Another thing, for example, what was Venus? Why does Venus have the strange spin that it has? We have many theories to explain it, why it spins so slowly and also backward from Earth. But wouldn't it be great to see the demographics of all these Venus-own planets? What if it turns out that they all spin like Venus? That would be wild.
Yeah.
Or maybe they're all tidally locked. That's another option. Maybe they all spin somewhere between Venus and Earth. I mean, that's all information we're going to gain from the exoplanet realm that we will never get for Venus, because we will never get the evolution of Venus's spin rate from Venus. It's not going to provide us that information. It's not possible. But we can get that other ways also.
Wonderful.
Otherwise, we just have to rely on theories like we do now.
Yeah, it's really exciting. And entering this realm of giant surveys of exoplanets, when you can sit down and scour through the atmospheres of hundreds or thousands of Earth-sized worlds orbiting on other stars, like this is our inevitable future, and it tells us so much about our own home. If people want to keep track of the work that you're doing, what's the best place to do that?
I guess that's a good question. I didn't expect you to ask that question.
How?
I don't know. I'm an academic, so I just publish papers,
I mean, I found your work on Archive, so I guess just search for your name on Archive.
Yeah, you can use Archive or Google Scholar. That's a really good way. I mean, that's where everything ends up nowadays. Yeah. They're very good at it. And maybe Microsoft Bing with their chat GPT will do the same in the near term.
That'll be interesting.
Maybe it'll even tell you what I'm thinking. You never know.
Yeah. Well, Michael, absolute pleasure to talk to you, and good luck. And when you do either discover life on Venus or at least get that flagship mission approved, let me know.
I will. Thank you so much for making the time also.
All right, take care.
Appreciate it.
Bye-bye. You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at university.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at university.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Maud Sue, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verabioff, Josh Schultz, and Andrew M. Gross, who support us at the Master of the Universe level. All your support means the universe to us.